do not forget to put it in the chat box. And also, do not forget to write your name in the chat box as well. Yeah, thank you. So, give me a few minutes while I share my screen for the feedback. Okay, going quickly into the first one. The first one had to do with force between point charges. Force between point charges. Now, from the force between point charges, we are able to see how to calculate the force between point charges, and also how to calculate electric field intensity, electric potential. Many of us were able to get our first and second question right, and even the third. The ones that people had problem with was the last question here. So I'll just run through the first set of questions and then we go to the last one. A very quick error that I spotted. A number of us, as usual, with many students doing this topic, forgot to square this distance here, this R. A number of us forgot to square it. Please, it is very easy to forget, actually. It's very easy to forget. I've seen quite a number of students making that error. But please, don't forget. Try as much as possible to build it into your consciousness, not to forget that this R is R squared. It's even trickier when you already have a distance that is in standard form. So you already have a distance of maybe 3 times 10 to the power 5. And then it's possible for someone to think that because there's already a standard form, you just get carried away and then forget to square it again. So a number of us had issues because we did not square that R. Now, some of us also had issues because we did not convert the R from centimeters to meters. I've said that severally. Please, always convert your centimeters to meters. It is not, it's not allowed for you to say you are looking for force, which is in Newton, and then you are using a distance, which is in centimeters. Centimeters and Newtons are not both. Only force is the SI unit. Centimeter is not the SI unit. So if you are calculating anything in SI unit, the unit of all components properties you are using must also be SI unit. So if you are calculating work done, for instance, SI unit of work done is watts. The unit of all the constituent properties you are using to calculate that watt must also be SI units. Please take note of that. So apart from that, there was no error there. The second one too was pretty good. Everybody, I think everybody got that also right. It was easy for us. We did, many of us, I see that many of us now are conscious about converting millicoulombs to coulombs. Okay, I think I saw one person who didn't do that. Converting millicoulombs to coulombs. It's good that we are now getting that consciousness. That's really good. 1,000 millicoulombs makes a coulomb. So please do not forget that. Do not forget that. And once you're able to do that, W equals QV, you get your answer. That was pretty straightforward. Number 3 and number 4 were also straightforward. Number 3, electric field intensity. You were given force and charge. Pretty simple. You just get your F divided by Q and you get your charge, 4 million. Number 4 also was the same. What I want to spend a bit time on is this number 5. Now I want you to just pay close attention to number 5. In the question that we were asked, the number 5 question said that we should find, let me get it. It said we should find the work done in moving a charge. He said, how much work is required to move a charge of 3 times 10 raised to power minus 5 coulombs from a point 50 cm to a point 20 cm. Now, please, if you read carefully the hint I have put there, please, I want you to take some minutes to just carefully read it. Carefully read it. In the question we were to solve, there was a charge that was moving, and then there was another charge that was static, stationary. Now, the work we are looking for is the work done on the moving charge, not the work done on the stationary charge. If something is stationary, that thing is not doing any work. We already know that. So it was the work done on the moving charge that we were looking for. And our W is equal to QV. That means in that place, our Q must be the moving charge. However, how do we get a V? Because we were not given V at all. Now, that is where the stationary charge comes in. You are trying to move a charge from a point to another point. Now, the charge you are trying to move is in the field of another charge that is stationary. You are trying to move a charge in the field of another charge that is stationary. So you find that if you are in that instance, there's an electric field intensity from or due to that stationary charge. So as you are trying to move a charge, it's like you're trying to overcome a field. You already have a force field somewhere. And then you are now trying to overcome, you are trying to bring something into that field. You have to overcome sort of, let's call it a force or something. You have to overcome the potential of that charge that's already there. So that stationary charge already has its own potentials around. You now want to bring a new charge into it. You have to be able to overcome that potential. To overcome the potential of the stationary charge. Now, in that instance, in that case, you need to know the potential at those points due to the stationary charge. So we have to find the potential at 50 cm, potential at 20 cm due to the stationary charges. Now, having said that, the difference between the two potentials is what we are now able to use to find the potential difference that we will now use in that formula to get our V. So, having said that, that's the hint. Now, I'll take you to the solution, how we solved it. Now, look at the solution. The potential at 50 centimeters due to the charge of the stationary charge. The stationary charge, as I said, is already an existent charge. It's already at a point. That means it already has a potential around it. So the potential that stationary charge has at 50 cm is what we found there using our formula for potential. V equals KQ over R. Do not forget to always convert centimeters to meters, as I said. Then we also found a potential at 20 cm, still due to that stationary charge. Now, the difference between the two potentials is what gives us the potential difference. So that means that when we are moving that moving charge, the charge we were moving, when we were moving it from the 2 points, we were moving it from a point that had a potential of 3.6 times 10 to the power 6 to another point that had a potential of 9.0 times 10 to the power 6. We now had to find the difference. It is the difference between these two potentials that we call potential difference. So once we're able to find that difference, we now know what our V is. So we can now say, oh, W equals QV. And then from there, we get our final answer as 162 joules. That is pretty simple. That is clear, but a number of us had issues. And I want to believe that as I have explained it now, that some of us, at least quite a number of us, will understand what I have just tried to explain again. So I want to specifically call on some of us. Daniel, The explanation I just made, how does it resonate with you?
I'm not quite sure, sir.
You are not quite clear.
Yes, sir.
Okay. Now, Chidindu, how does the explanation resonate with you?
I understand.
You understand?
Yes, sir.
Okay, good. Now, let me explain again for those who were not quite clear. Here we are. This is the question we were asked to find. And this is the hint I put up there. We have a charge that is stationary. And then we have a charge that is moving. You want to move the charge, the moving charge, you want to move it from one point to another. So from our formula for work done, let me go back to mechanics a little bit. Work done is force times distance. Our distance, we define distance as change in length, more or less. Change in length from one point, between one point and another. So in this case, that distance that we use in mechanical work done is what we call potential difference here. That's a difference in potential, change in potential. So Daniel, that means that we need to find a change in potential because W equals QV. But we cannot find a change in potential if we don't know the original potentials. You clear with that? So we need to know the original potentials. And the formula for potential is V equals KQ over R. Now, how do we know the original potentials? The original potentials are the potentials due to the static charge. The static charge is the one that more or less owns that area around it, is the owner of that area. So it's like you trying to move something into a place where there's already another existing charge. So you have to be able to kind of overcome that influence, that potential of that existing charge. So we have to know the potential of that existing charge at those two distances. So having done that, then we can now find the difference between the potentials and then now say, okay, this is the potential difference. And then from there, we are able to get our work done. Now, work done is force times distance, mechanical work done. But in this case, it is charge times the potential difference. And the work done, as I said, you are not doing work on a stationary charge. You're only doing work on a moving charge. Something has to move before you can do work on it. So if you're doing work on a moving charge, then the moving charge is the value you must use for your Q. And then the potential difference is the difference between the two potentials that you found. The potential difference is usually exerted due to a potential is exerted due to a stationary charge. We cannot find a potential due to a moving charge because if something is moving, it's in motion. You cannot be finding potential of something in motion. What distance will you use? It's in motion. Before you find the one at a point, it has moved. So it's the one that is stationary that you can use to find the potential at those points. But you need to now use the moving charge to find the work done at the 2 points. So I'm going to just stop sharing this screen for a little bit. I will come back to it just so that I can see your faces and know if you really understand. Daniel, just tell me in the chat box, how well do you understand it now? Or give me a sign to show how well you understand what I'm saying. Okay. All right. Who else still, you understand, that's good. Who else still has a problem with the explanation, particularly for that last question? Anybody? Okay, nobody. You all understand better. You all understand better. That's good. That's good. Okay. We are now going to go to the next set of assignments that we had. That's the one on capacitors and capacitances. Capacitors and capacitances. That's the one we are going to now. Yeah. Okay, so feedback lesson on capacitors. We also had some work to do there. We were asked to find energy stored in a capacitor in the first instance. That's the first thing we were asked to find, energy stored in a capacitor. As I explained in the note, energy stored in a capacitor has different formulas based on what you are given. It could be half QV, it could be half CV squared, and it could be Q squared over 2C, whichever you are given. So in the question, we were given the capacitance and then the voltage. You were asked to convert the capacitance, or you have to convert the capacitance from microfarad to farad, and you're already given the voltage. And then you must remember the half, because the energy stored is stored over time, and you are looking for you need to be able to find the average of the initial and the final. Initially, the charge was 0. I mean, the capacitance was 0. The voltage was 0 initially. Then it now accumulates over time. You must find the average. If you look at the notes, you understand that. Now, let me come to number 2. A number of us had issues here because some of us treated capacitors in parallel as though we were dealing with resistors. So some of us, in looking for our capacitance in parallel, we treated it like resistors in parallel. Please do not make that mistake. Capacitors in parallel are treated like resistors in series. They are not treated like resistors in parallel. And then capacitors in series are treated like resistors in parallel. So what you do for capacitors in series is what you do for resistors in parallel. Do not forget that. Do not make the mistakes again. Now, having said that, those of us who were able to do that, where we got our answer straight off, there was no problem. And then in number 3 too, there was no problem for those who knew how to treat the capacitors in series, no problem. But we had a little bit of problem in number 3 too, because some people got microfarad, 3.75 microfarad, and came to use the 3.75 only without converting into farad in finding their 3.2. Now, that is not correct. That's what I said earlier. SI units. If you are solving to get SI units, the unit of all the component properties must be in SI. So 3.75 microfarad. Microfarad is not the SI unit. It's a unit, but it is not the SI unit for capacitance. So what that tells us is that before you can now use that 3.75 in another formula where you'll be getting SI units, you must convert that 3.75 to its own SI unit. That's 3.75 times 10 to the minus 6 microfarad. Those who did that had no problem at all. But a number of people did not do that. Now for number 4. Number 4 too is quite easy. Energy stored in a capacitor. You were given the capacitance, and you were given the charge, capacitance and charge. So you could have just used half QV, but half CV squared. But I decided to now just show you another route. I now decided to use my own values given to find my potential difference. It's easy. I also wanted to use this formula to take us back to what capacitance is. Capacitance. Let me ask somebody who can define capacitance for us. I'd like someone to quickly define capacitance. Let's see who we have in the class. Bess, I have asked you to unmute. Please unmute yourself. Bess, I'm waiting.
Yes, sir.
Yes, what is capacitance?
Is the ratio of charge in an electric. Is the ratio of charge.
Is the ratio of charge to something. Charge to what?
So electrical charge in the system.
Charge and electrical charge, you are still saying the same thing. Radio of charge to what? Let's go to someone else. Inioluwa, how do you define capacitance?
Capacitance is the ratio of charge to potential difference.
Thank you. The ratio of charge to potential difference. That's good. Capacitance is the ratio of charge to potential difference. So saying that, we know that C equals Q over V. That means I can easily find V. Question gave me Q, gave me C. So I just found my V, and then I now put it back into the formula for energy stored in a capacitor, and I got my answer as QV over 2. But if you had done CV squared over 2, you still have gotten the same answer, 33.33 joules. And that was it. That's the last. I think that in this second set also, this last one was where most people didn't get it right. But many got the numbers 1 to 3 right. So that's good. That's good. It's good to know that we are all getting a hang on what we are doing so far. Koima, thank you. Thank you. Now, I'm on the dot of 30 minutes exactly. There are just 12 of us in class today. Now, we are wrapping up, at least for the next 2 weeks. Congratulations. Very soon your exam should hold. We are waiting for WASE to give us their guidelines, their timetables. So some of you will be back in school soon. But do not forget, I have been having issues, questions about what to study, what should I study, what should I read, and all that. Do not mix anything up. All you have done between years 10 and 12 up to this point, if you have been able to master those ones, you have more than enough to score an A1. More than enough to score an A1. Now, if you have now gone ahead to read up what I said you should read up on rockets, on satellites, on basic electronics, semiconductors, if you have gone ahead to read those up, you have increased your chances. You have boosted your chances. But all those little things that we have not done, all those little pieces, those end of your table that we did not really do in class, they are not a heavy requirement for your WASE. Now, why am I saying this? I don't want you to, in the quest of trying to do everything in your textbook, now begin to lose sight of the very cogent things you need to know. All the things we have done, motion density, projectile work done, electricity, those ones, they will cover at least 90% of your WASE questions, if not even more, the minimum 90. I would prefer students to master those ones and know it well. And then if you're able to do rockets, rocket 2 is easy. Rocket and satellites is particularly easy because there's no calculation. It's just reading up functions, parts, states uses, that's all. If you're able to do that, that is fine. That is very fine. But as you come to school for your exam, I want you to be relaxed. Know that you have more than enough. Relax, don't be agitated, and all will be well. So that will be all for today. Hope to see you whenever the school says we should resume or whenever the lessons start again. Good to have you. Good to have you. Prepare for your next class. Bye-bye.